Welcome to our presentation on optimizing for the shortest path in denoising diffusion models. My name is Ping Chen, and today we will explore how we can enhance the performance of diffusion models by optimizing the shortest sampling path, aiming to reduce computational costs while maintaining high-quality outputs. Let's start with an overview of traditional diffusion models. Diffusion models, especially those based on the denoising diffusion probabilistic models, DDPM, have made remarkable strides in image generation. DDPM works by progressively adding noise to clean data through a Markov chain, transforming an image into Gaussian noise. To generate a clean image, we reverse this process, gradually removing the noise through multiple denoising steps. However, this process typically requires hundreds or even thousands of steps, which is computationally expensive and time-consuming. Now, let's take a look at the challenges associated with this process. To address the issue of slow sampling, accelerated methods like DDIM have been proposed. DDIM speeds up denoising by estimating the clean image at each step and skipping intermediate steps through a deterministic path-jumping mechanism. This introduces the possibility of different sampling trajectories. If we assume the noisy input is derived from clean data, then logically there must exist an optimal path that minimizes the reconstruction error. This insight brings us to the idea of searching for the shortest or best sampling path using principles from graph theory. However, we face two major challenges. Complex noise variability. The inherent diversity in noise makes it impractical to build an explicit graph to find the optimal path. Inefficient sampling paths. Even when optimal paths are identified, they often require many steps, leading to high computational costs. To overcome these limitations, we propose ShortDF. Instead of building an explicit graph, we treat the model's parameters as defining an implicit graph. Our approach performs path compression using this implicit structure to balance denoising quality and efficiency, reducing the number of required steps significantly. Now, let's dive into the method. Imagine we have many possible paths, and each path corresponds to a reconstruction error. We define the optimal reconstruction error as dist. To achieve efficient sampling, we assume that single-step denoising can approximate the optimal multi-step path. Moreover, we leverage earlier denoising steps, denoted as step K, to guide later steps, denoted as step T. If we already have an optimized result at step K, and we know how the error would propagate between steps T and K, we can update the result at step T using information from K. This has the flavor of reverse graph construction. By treating these error propagations as edges in a graph, we apply shortest path relaxation ideas. The result at step T is continuously updated based on better information from step K, compressing the path while preserving quality. Let's now look at how this method is optimized in practice. We draw a connection between our method and graph theory. The relaxation operation in shortest path algorithms is analogous to minimizing a conditional loss. Each update in the model is like adding an edge in an implicit graph to compress the path. When step T is relaxed using step K, it's equivalent to adding a new edge with a better reconstruction estimate. To train this setup effectively, we propose a multi-state optimization strategy using three models: a base model, a graph model, and an EMA model. All share the same architecture but differ in their parameters. The graph model represents the pre-update state of the graph and is used for calculating propagation errors. The base model is actively trained. It represents the current graph formed by all relaxed paths. The EMA model is the exponential moving average of the base model, providing stable reference points. With this setup, each path from any time step T to the final image approximates an optimal sampling path. This directly supports our assumption that single-step denoising approximates the best trajectory, ensuring both theoretical soundness and practical effectiveness. Let's now look at our experiments and results. We benchmarked ShortDF against DDIM across CVPR10, Celeb A64, and LSN churches at 256 resolution. Our results show that we can significantly reduce the number of sampling steps while maintaining or even improving output quality. For instance, on CVPR10, ShortDF achieves better results in just 2 steps compared to 10 steps with DDIM. To summarize our contributions, we establish a theoretical connection between implicit graph optimization and deep learning updates. We propose a methodological framework that combines residual propagation and implicit path compression. And finally, we demonstrate significant gains in generation speed, image quality, and training stability. The code for ShortDF is available at the link shown on the current slide. Thank you very much for listening. I'm happy to take any questions you may have.